So welcome back to part 3. In the previous part, we were looking at a very special example, and we saw that somehow eigenvalues and eigenvectors will kind of tell us something about a dynamical system. And I want to kind of talk about what happens more generally. So here's kind of the assumptions that we're making. Not every matrix will have these properties. So if it doesn't have these properties, then you have to do a little bit more analysis. But we're not going to worry about this. This is going to be kind of our assumption when we're doing these. So A will be a diagonalizable matrix. A has n linear independent eigenvectors, v1 to vn, corresponding to its eigenvalues, lambda 1 to lambda n. And we're going to order the eigenvalues so that they're in decreasing or non-increasing order when you take absolute values. Okay, so let's kind of then use this setup to figure out what things we can say. Okay, so since V1 through VR, that should be a Vn, not a Vr. Since V1 through Vn is linearly independent, they form a basis for Rn. Okay, so that means that Rn is equal to the span of the vectors V1 through Vn. Now, what that means is that we can take any initial vector of our system and we can rewrite it in terms of our bases, right? So it's rewritten in terms of our bases in the following way. C1 times the first vector plus C2 times our second vector, V2, and so on, up to Cn times our last vector, Vn. Okay. So this is, maybe I'll write this here. So what we're doing is using the eigenvector basis. Okay, so once we have our eigenvectors, we can use it as a basis, and we can write our initial vector in terms of our basis. And then what we can do is figure out, well, what happens when you take that vector x naught and multiply it by a? Well, using the same argument that we had before is you can multiply a in, and what you're going to get is C1 times a times V1. But remember, V1 is an eigenvector, so you get C1 times lambda 1 times V1 up to Cn times lambda n times Vn. Okay, so that's what happens after one iteration, but then you can keep reiterating this process, and eventually you're going to end up with, for any k, you're going to end up with C1 times, oh, I don't know why that showed up there, let's get rid of that, C1 times lambda 1 to the k times V1 plus C2 lambda 2 to the k V2 up to Cn lambda n to the k times Vn. Okay, so you get a kind of a nice formula for the kth term in this sequence by rewriting every thing in terms of eigenvalues and eigenvectors. Okay, so I think that's what my point here of my note is that the eigenvectors and values determine the vector x to the k. And of course, the other piece of information is the C1, C2 up to Cn, which comes from the initial vector that you're starting with. Okay. Now, the observation then that we want to use is that suppose that this vector, because this is not vector, eigenvalue is the largest and it's actually greater 1 or greater, and the rest of these eigenvalues are strictly less than 1 when you take the absolute value. Well, what happens in that case is that for large k, when you take large powers of these numbers here, they all go to 0. So your function x to k eventually becomes approximately C1 times lambda 1 to the k times V1 plus some number 0. Since lambda I to the k approaches 0 for I going from 2 to n. Okay, and so this general situation I just described is actually what's happening in the first example, because let's go back. What did we do? We had our matrix, it was diagonalizable. We had a basis, we wrote the x naught in terms of the basis, and then we were able to describe the case value in terms of the eigenvectors and eigenvalues. So that's kind of what's happening for large K. And we'll take a quick pause here, and then we'll talk about what some of the graphical meanings of this is.